Thank you. Okay. Hi, everyone. So I'm Urmila Chadayammuri. I'm a PhD student in the Department of Astronomy at Yale University. Specifically, I am a computational cosmologist. And so over the next few minutes, I'd like to tell you what that means, what we do, how we do it, and why it is exciting. So astronomy has always been a very data-driven field, right? We only have this one universe. We can't go ahead and perform experiments the way other physicists do. In a lot of the sciences, you have a dichotomy between theorists and experimentalists. In astronomy, you have theorists and observers because there is this one universe. We collect a lot of data. We currently live in the era of large surveys where we observe the entire universe in a bunch of different wavelengths, ranging all the way from the radio and submillimeter, like the Planck satellite, I'll talk about that more in a minute, to through the optical, which is what we're used to all the time. So the Sloan Digital Sky Survey has created a map of a very large volume of the nearby universe in the optical. And really, we probe the universe all the way out to X-ray wavelengths, where we see the most energetic processes today. What are some of the things we can do with this? So as a cosmologist, right, I'm interested in the universe as a whole. What is it made of, and how has it evolved since its birth? So when we look at the universe with something like Planck, which is a microwave telescope, what we actually see is what's known as a cosmic microwave background. So this is also known as the echo of the Big Bang. It's light from when matter and light, so protons and electrons and photons, separated from each other for the first time when the universe was about 380,000 years old, which is basically baby universe, because today it's like 13.8 billion years old, right? So I can measure the temperature of the cosmic microwave background in every direction around us in the sky, and it has fluctuations of the order of 1 part in 10,000. Very small fluctuations in the temperature that actually correspond to fluctuations in the density at the time that the light left, its source and arrived. And it started making its way over to us. So basically, when the universe was 380,000 years old, the fluctuations in the density were of the order of 1 part in 100,000. Then we can look at something like the Sloan Digital Sky Survey and measure the density of the universe today, right? How are galaxies distributed? Their number counts are essentially what you see here. And at this point, the density of the density within a galaxy, for example, within the Milky Way, is about 1 million times larger than the average density of the universe. So these fluctuations have grown tremendously between when the universe was very young and today. And so this evolution of structure, this growth of structure, is something that we can absolutely predict to first order using just our understanding of gravity. And so what you see here is a simulation from our group. So this code was written by my academic grandpa, Andrei Kravtsov. He's a professor at the University of Chicago. This is what we call an n-body solver. So you're just solving the equations of gravity for millions of particles, right? And actually, in this particular case, this is a grid-based solver, but essentially for millions of units, you're solving just the equations of gravity, and starting from these initial conditions motivated by something like Planck, you end up with this structure known as the cosmic web, a very filamentary structure with these nodes corresponding to groups and clusters of galaxies. And this is very much what we see when we look out with something like Sloan and construct a catalog of what the universe looks like today. So what is the universe made up of? So basically, through a bunch of different clues, we have figured out that the universe is mostly dark, right? Everything that we are familiar with, the baryons, they constitute about 4% of the energy budget of the universe. Something called dark matter, which has gravitational interactions but nothing else really, constitutes 23% of the energy of the universe. And the remaining 73% is dark energy, which is some mysterious repulsive force which is causing the expansion of the universe to accelerate. What are these? We don't really know, right? And so what we can do is theorists can come up with interesting ideas for what the dark matter and dark energy are made up of. We can convert those into effective equations that then the numerical solvers can go ahead and solve and make predictions for what the universe would look like today. Then we can compare that to observations and see how good was the theory in the first place. So you notice that the nodes in that cosmic web were, the biggest nodes are called clusters of galaxies. And so this is basically what I study. They're very important to cosmology because back in 1933, Fritz Zwicky, the Swiss astronomer, first came up with the concept of dark matter or dunkle materia when he was looking at the movements of galaxies in the Coma cluster, which is a nearby cluster of galaxies. And so basically, for example, in the solar system, you can measure the speed of a planet and then the distance of the planet from the sun. That basically tells you the mass of the sun. You can do the same thing in a cluster of galaxies to see how, to look at the speed of galaxies as a function of radius and convert that into how much mass is enclosed as a function of radius. And there was just much more mass than there were stars and gas. And so he was like, well, there has to be something else, right? And people were like, oh, maybe just our formula for gravity is wrong. And like, this is called modified Newtonian dynamics. People just wanted to change gravity, but leave most of the matter in the universe normal. In 2005, we had this discovery of the bullet cluster, which is so exciting. And so basically what happens here is, what you're seeing here is a merger of two galaxy clusters, okay? So they basically just like rammed into each other, and actually they've already, moved past. The stars have already moved apart from each other. If modified Newtonian dynamics, or MOND, were true, the stars would be in the same place as the gas, because if you look at all the baryons in a cluster of galaxies, about 10% of them are in stars. 90% of the baryonic matter is in the form of gas. And now, stars are small and far apart. And so if you have two galaxies colliding into each other, stars don't really run into each other. Stars pretty much just sort of like walk past each other, right? But the gas is a fluid, right? It has inelastic collisions. And so the gas from one cluster and the other would just clump together in the middle. If the stars were following the gravitational potential of the gas, they would be sitting in the middle too. But instead, they've passed away, they've passed on, right, to these blue areas, whereas the gas in the pink is stuck in the middle. And then people use gravitational lensing to figure out, well, where's the mass distributed? And indeed, the mass was mostly where the stars were. And so there was just no way that the mass had to do with the gas, and it was not about modifying the rules of gravity. It was that there was an extra source of gravity that we couldn't see in the electromagnetic spectrum. Now, in the 2010s, we've gotten to the point where we can actually use our simulations of large-scale structure and essentially count how many clusters of galaxies there are of different masses in a given volume. And basically, cluster counts are a prediction that we can make on the level of a few percent. And cluster counts are what we use now to constrain various cosmological parameters. So basically, you go from two different directions, right? As I mentioned, we only have one real universe, but we can have any number of simulated universes. Well, insofar as we have, computation time. And so here's what you do, right? You have a model for cosmology. You have to include your baryons because they do all kinds of wonky stuff. I can talk about that more later. And so, you make your predictions for, how many clusters you have as a function of mass, or how closely clusters cluster together. So there's a lot of stuff we can talk about, but you can make all these concrete predictions from the simulation side, and then you go measure stuff in the real universe, and you basically compare the two and say, how good was your model? So as I said, the dark matter gives you your first order prediction, but once you start looking at either small things like satellite galaxies around the Milky Way, or if you look in real detail within a galaxy or within a galaxy cluster, so on these smaller scales, you're not going to get away with that. You have to explicitly model radiative processes in the gas, specifically solve the fluid equations for the gas correctly, and have a good model for star formation and feedback from stars, so supernova explosions, mass loss from massive stars. I specifically study supermassive black holes and the accretion disks around them and the energetic processes from that. You want to include all of this stuff for your predictions to really start looking like your observations. People use a bunch of different codes for this purpose. So like I said, I'm in the art team. Every time I compile my code, I type make art, which makes it feel, pretty. But there's a bunch of other codes out there. So you have particle-based codes like Gadget. Arepo is a moving mesh, so it's sort of the middle ground between a grid and particles, which are Lagrangian solvers. So there's many different ways we can look into this. All the different codes have their pros and cons, and so code comparison has sort of become a field of its own to see like what can you study well with different codes and how can we mesh the results together. And so specifically, adapt. Adaptive refinement is cool because adaptive refinement is cool because it allows us to achieve really high resolution in the areas which are very dense and therefore interesting. As you notice in the cosmic web, most of the universe is like empty stuff. So you don't want a bunch of resolution in that area. You're just wasting computational time. Instead, you can basically reduce the size of your grid element when you reach a certain density criterion. That's the basic premise of adaptive mesh refinement. And that's how we managed to resolve the very center of a cluster of galaxies. That's one galaxy versus the scale of this entire simulation is like 100 million parsecs, where a parsec is about 3 light years, right? So 300 million light years versus a galaxy which has the size of like a few hundred light years, right? So we achieve a dynamic range of about 10 to the 6 in spatial scale. And lastly, the beauty of these simulations is that we can really start to look at the universe in all these different ways that we can then go out and observe in various wavelengths. So we know what the dark matter evolves like, but then we also, we can model what the gas looks like. We can model its temperature, we can model its entropy, which is a convolution of density and temperature. We can actually, the latest frontier these days is the evolution of metallicity, because metals are mostly, astronomers call anything heavier than helium a metal, but all of that stuff, all the heavy elements are processed within stars, and so transporting them is actually also a good test of, what are the physical processes that happen within a galaxy or galaxy cluster. And of course, we model stars and star formation. So basically, we're at a point today where using adaptive refinement, either in grid-based codes or particle-based codes, we can make predictions for what the universe looks like in all these different wavelengths that we can then go and measure with real telescopes and continue to constrain our cosmology and better understand dark matter and dark energy. Okay, I think that's all I have today. This is my closing slide. Thank you.
Thank you, Urmila, everyone. Thank you.